Hello, my name is Einar Andre and I work for Statoil's CIO as a lead analyst on digitalization. I have more than 30 years of experience as leader and software architect in the high-tech and service industry. You find my full professional bio on LinkedIn. This talk has a long history and to some extent it distills some hard-earned insights. The talk has also been presented as systems of action transforming operational events into feasible actions. The talk will aim to address the following questions. Why do we need operational decision support systems? And what does it take to build such systems for an hazardous industry? Before we start answering those questions, a few words about Statoil. We are an international energy company with operations in plus 30 countries. We have 40 years of experience from the North Sea and some 20,000 people. We are headed out of Norway. So, what has motivated this talk? Basically, it boils down to two things. Firstly, being part of a hazardous industry, we know that failed decisions can go utterly wrong. How wrong was illustrated by the BP Deepwater Horizon accident in 2010. They were drilling a difficult well in a difficult reservoir. They had the latest and greatest technology at hand. But in the end, the human operators did not understand system messages and alarms before it was too late. The first indications of that something was very wrong came 50 minutes before the blowout materialized and hell was loose. Secondly, we must begin to accept that we, the humans, are the weakest point. In one way, our brain is the planet's most sophisticated decision maker, but it is also the most vulnerable one. Emotions trump facts. We have limited processing capacity. We need to rest. We are easily disturbed, and we are extremely inconsistent across exemplars. We see the same patterns unfold in the drilling chair, in an airline cockpit, or a hospital emergency room. We humans loses our situational awareness and develops tunnel sight. We are not able to see the forest for the trees, and we most often make huge mistakes. So, how can we provide technology that help humans to perform better, particularly in highly dynamic and stressful situations? How can we compensate for our inherent weakness? But since the talk is rooted in an Internet of Things context, it will be useful to provide some perspectives on things in context of the oil and gas sector and how our understanding has evolved over the last decades. 20 years ago, back in 1995, software as we today think of it was an alien concept. The software on the Troll A was basically its human operators. The Troll A is famous because it's the largest man-made moved object in the world. Today, the Åsgard subsea compression plant runs on software. It will not be able to fulfill its missions without its optimization algorithms and control programs. Looking into the future, we might find installations like this one. Installations we in Statoil like to call the subsea factory. In context of things, the subsea factory is nothing more than an internet of critical things forming critical systems. Critical things and systems are things and systems where failure might lead to accident and even loss of life. Example of what we call critical things includes, but are not limited to, pressure vessels such as boilers and oil wells, industrial instrumentation and control systems, and medical devices like pacemakers and infusion pumps. For critical things and systems, the key is to understand the practical impact of system criticality. In a hazardous industry, there will always be things and functions that falls into the category of mission or safety critical. The challenge is that these things defines how the whole need to be engineered and operated. Being able to isolate and classify things correctly becomes paramount. Applying the practices for non-critical on something that is safety critical is just as stupid as doing it vice versa. We will try to use a case study to illustrate basically what it means in practical terms. We have picked drilling, and there are two reasons for that. Firstly, there is a desire in the industry to raise the automation level in drilling, and secondly, it is a critical and demanding process that can be easily explained to people outside the industry. Drilling is by all practical means a manual process, where the driller from his chair controls three parameters: the rotation of the drill string, the mud circulation, basically maintaining the stable hole and transporting cuttings, and finally the weight on bit, basically with what force shall we crunch the rock. The objective is to drill as fast as possible, while at the same time maintain the stability of the hole. Adding too much force might lead to destruction of formation. Adding too little might lead to influx of formation fluids that can lead to blowout if not detected and handled. The driller faces a rather chaotic work environment, where a lot of things happens. The driller must plan actions ahead in time, while at the same time assess feedback from previously executed actions. The main challenge is to understand what is the best possible action to take. To support such decision making, adding more screens with more data is not what is needed. What the driller needs is some sort of contextualized advice about the available options. To produce such contextualized advice, we in Statoil define what we call systems of action. A system of action is a software component that can sense or observe a phenomena, process of a machine, process observations and search for anomalies, undesired state changes and other deviations that must be dealt with, plan and execute actions to bring the observed phenomena, process or machine back to its desired operational state, and finally monitor effects of actions and replan if actions did not have the intended effect on process or state. The capabilities described in systems of actions materializes in what we here call a support mechanism, the driller's body. The job of the driller's body is, of course, to interpret the state and information from the drilling control system and basically then provide contextual advice to the driller in the chair. To build such body, we need to combine a lot of technologies. We have historical data, they might be real-time, and they might be records about, say, experiences from previous drilled wells. It might involve the development of simulators and use of simulators. And finally, we have what we call the action planner and scheduling machine that transform basically the insights into actions and recommend them to the operator in the chair. All of this might lead to usage of rather sophisticated models and technology. What technology to use depends, of course, on the actual body and our ambition level. We can also describe what such body does in terms of capabilities organized into a stack model. Each layer addresses a specific function. Starting from the bottom, we have to answer questions like what are we measuring directly and with what accuracy? What can we infer about performance and change in the physical system? What do we know for certain and what are we estimating? What is the process state and where is it heading? And basically, what is the best action to take, either for control or safety or for the best possible business outcome? Of course, the whole thing leads us to a rather more sophisticated technology stack, and where we need to deal with sensors, we need to deal with machine learning, we might need to deal with the modeling of physical models, and planning and scheduling algorithms. We might even see the benefit from game theory. When it comes to realization, the agent paradigm appears appealing. Agents has goals, deals with uncertainty, and they can learn from their actions. Agents are also supported by a large body of literature and knowledge we can tap into. The effects we now can see is that the solution to one challenge leads to new challenges. We can see what happens when an industry becomes software dependent. We must start asking questions such as what parts are critical, what are the impact of failure, how to protect the critical parts against cybercrime and cyber war, and how to deal with mechanical failures. It basically boils down to how to best build what we can call trustworthy software. How many of you would have enjoyed hanging in that rope if you know it was built or created by a mediocre programmer? I would certainly not. So, what can we say about software? But before we start on software, we need to take a look at the world before software. In the old days, we had tangible logic, and we had no cyber threats. Logic was built the way it was designed. Test and verification of the system was possible. Software, on the other hand, comes with two unique properties. Firstly, software cannot be inspected and tested in the same way as analogous components. Secondly, all signals are threaded through one single element, the CPU, with unknown execution sequence. For high-integrity systems, these two properties define how we must engineer and manage the software. We'll now just cast some light on a handful of specific challenges. The first one is common mode failure. Common mode failures are caused by dependencies that causes a coincidence of failure states in two redundant challenges that leads to an overall system failure. The Ariane 5 test launch is a good example of what happens. The second thing is, of course, malware, viruses, and hacking. This is a topic worth a presentation in its own right. The main point here is that this is software created to cause harm. It's software that exploits weaknesses in human character and in technical designs. We want to mention two horror stories, like the Stuxnet and the Iranian centrifuges, and the Saudi Aramco hack. What we know is that there is a war going on, and that we must take into account when we design software for critical systems. It's too late to begin thinking of this after it's installed and the systems are commissioned for production. This, of course, causes a major concern when elderly control systems that was developed in the 1990s become exposed to the internet. Thirdly, human factors. It's normal that humans make mistakes. It might be by commission, omission, or carelessness. It does not matter that much when the mistake is done. We should also know that the mechanisms intended to create safety might be misused. Think of the safety lock on the German Wings airliner that was taken down by a suicidal pilot that exploited what was a safety mechanism in the first place. Therefore, we need to ask ourselves how to minimize the effects of human errors along the whole life cycle process, from concept to operations. Finally, blurred boundaries. This is probably the trickiest part to talk about. Software, as a material, invites us to blur its boundaries. This is the result from the fact that software is sequences of logical instructions, instructions that have no boundary per se. One way to illustrate the point is to take a look at how different stakeholders think of the software they are involved in building and using. Architects think and design in terms of hierarchy and layering. Programmers think and design in terms of threads of execution. Users need software they can use to solve real-world problems. And operational staff, of course, need to make sure that all systems are running. We have stakeholders with very different priorities and needs, and some of those priorities and needs might even be conflicting. Up to now, we have outlined the effects and challenges of becoming software dependent. We have also provided examples of topics and issues that must be dealt with. The next step is to take a look at the two tools we have at hand. The first tool is systems engineering. Systems engineering is the art and the science of building systems, where the focus is on functional decomposition and integration of functions. To quote Derek Hitchens, a leading British systems engineer and thinker, systems engineering is a systematic problem-solving technique. It comes with a long track record. It was basically systems engineering that brought mankind to the moon and back again. It was systems engineering that made the Troll-A platform possible. What we have to do is to forge design thinking with high-integrity system practice into the architecture-centric, risk-based methodology. We do not design non-critical functions as they were safety-critical, nor the other way around. Architecture is one of the strongest mechanisms and techniques we have dealing with complexity. Systems architecting boils down to divide and conquer. One of the key challenges is to bridge requirements between different architectural representations. How basically to interpret between those two things. How should we deal with, say, physical system behavior in a safety critical function? Systems architects' focus is on boundaries and interfaces. That's been the case for a long time and it still is. Standards represents insights from the past. Use them and continue to develop them. We can learn a lot from the DO178C addressing how software in the aerospace industry is developed. Finally, and last but not least, we need to adopt evidence-based verification of both safety and security functions. Safety and security requirements are first-order design constraints that must be addressed up front. Safety cases is a good way to demonstrate that the requirements are met in the best possible way. Okay, to sum up, the first thing is that things run on software, and critical systems are built from critical things. There is a huge benefit from using software to support human decision-making, particularly in highly dynamic domains. To do so, second and third order effects must be analyzed and understood. We must also remember that the more advanced functions we want to implement in software, the more rigorous must our methodology be. Finally, the inherent complexities we face can only be addressed using a holistic architecture-centric systems engineering practice. A practice where we forge design thinking, basically placing the human needs first with high integrity system practice. With this, I say thank you for listening and watching. I hope you enjoyed the tour. If you want to give me feedback, you are free to do so. Email address is on the slides here, and you can find me on LinkedIn. Thank you again.